All right, back to work. During the break, I got a couple of technical questions. Why a function is surjective or not surjective? I'm very happy to answer during the break, but I'm happy to answer now because maybe this is a doubt that everyone has. Is there anything you want to ask?
Yeah.
Yes.
So it's the reflexive thing for division.
Yes.
Divisibility. I just don't quite understand how it's like
yes.
You have a set like of natural numbers cross natural numbers.
Yes.
X is a factor of y. That would be reflexive.
All right. So we have to start from the beginning. So this is the relation we are discussing. All right? So let me write here. Let's make sure that we understand it. So as always, we make the example of a few pairs that are in the relation and a few pairs that are not. All right? So this is z plus, which means 1, 2, 3, dot, 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 forever.
Like if they were tuples.
Yes. No, what do you mean tuples?
So if it was like.
And then we have this one. This means divide. The first one divides the second.
I meant like if it was a set of tuples.
A set of tuples.
So like z cross z or n cross n. So like one, like.
So.
1, 2. 1,
So this thing here, can I change the name because the bar is confusing? Let me call it divide. So divide is a subset of z plus across z plus. Is this what you meaning?
Yeah.
Yes. So divide is a subset, is a relation binary on z plus. So it's a subset of the Cartesian product. So let's write a few pairs that are there and a few that are not. We did it before, but we do it again. All right? Or you want me to take the one that we did before?
Whatever's easiest.
We have it here, right? We said the 7 divides 7, 2 divides 4, 9 divides 27, 3 does not divide 5, 5 does not divide the 3. All right, so this is the relation we are playing with.
I think 4 doesn't divide 2 though.
4 doesn't divide.
So
Very good. So if we want to write it, we write 4 doesn't divide 2. All right. So now we want to show that this is reflexive. What does it mean to show that this is reflexive?
Show that for any of those pairs, if x divides y, y divides x.
No. That would be symmetry.
Okay.
Thank you, whoever said
We're
it.
good.
We solved it. Fantastic. All right. So, partial order. Do we have to say anything more about partial order? Or you are sick and tired of it? So, an hour on a relation is more than enough, right? So my academic career has been studying a relation which is called narrowing. And I've been studying it for the last 25 years or so. So we can spend more than an hour on a relation. All right, so the next relation I want to discuss is called equivalence. So, when we did order, I said we studied order because when things are sorted, it's much easier to find something. Why we study equivalence? So if I ask you if 2 plus 2 is equal 4, what would you say? You would say yes up to this point, right? So 2 plus 2 equal 4. If they are equal and I underline that, Do they remain equal? Of course. Thank you. Is it true? So, if I paint it in red, let me see if I have a red pen. You understand where I'm going, right? Where am I going? If you have two equal things and you massage them in the same way, they remain equal. It's not that one change, right? So now I paint it in red and they remain equal, right? So, what if I quote them? Do they remain equal? Of course not. Put it in your favorite programming language or any other, of course that they are not. If you have a string, and this is a string is made of 3 characters, and this is a string made only of 1. So this is enough to say that they are not equal, right? So sometimes when we talk, we are a little bit slow. And most of the time is fine. In fact, up to this class, you would have swear that 2 plus 2 was equal to 4. And as soon as you take the exam here and you move to the next class, you will swear that 2 plus 2 is 4. But for this short period of time, you want to be a little bit more precise. This is very interesting for a computer scientist, more than a mathematician, because this really applies to computing, right? So here, we don't say that the 2 plus 2 is equal to 4. What we want to say is that the value or the result of 2 plus 2 is equal to the result of 4, or 3 plus 1. All right? So if we want this degree of precision, because sometimes we need it, we talk about equivalence. And so we say that the 2 plus 2 is equivalent to 4. Now, even in class, even when I talk, I'm sloppy, so a lot of time I will say equal rather than equivalent. Except when we are specifically discussing the relation. And then the relation is a little bit more complicated. And so, what is an equivalence? An equivalence is a relation which is reflective, symmetric, and transitive. It has these 3 properties, we say that is an equivalence. So before, when we had an order, partial order, we would denote it sloppily with this one, right? And so when we have an equivalence, typically we will denote with this one. When you see that wiggle, means that I'm telling you that the relation is an equivalence. So you know that has these properties. So let's look at an example. I'll take again Z, and I say that X is related or equivalent in this case to Y if X modified is equal to Y modified. You remember what is mod, right? You divide it and you take the remainder. Alright? I can do another relation of students and say the student X is equivalent to student Y if X and Y were born in the same month. Should we verify that these are equivalences? The first one or the second? Let's do the second, which is more intuitive, right? If X is a student, if X is born in some month, is X born in the same month? Right. It's so trivial that we laugh when we say it. If X is born in the same month of Y, is Y born in the same month of X? Of course. So it's symmetric also. It's transitive. If I am born the same month of you, and you are born the same month of him, I am born the same month of him? Yes. And so it's also transitive. So being born in the same month is a relation that reflects symmetric and transitive, so we say that this is an equivalence. We will study algorithms later on, such that we have to consider this notion of equivalence. All right. So, if you have an equivalence, we have this notion of equivalence class. What is the equivalence class of some element? The set of all the elements that are related to it, or equivalent to it. Right? So, for example, talking about the student in this class, suppose that when we look at hair color, we say there is a dark, blonde, or red. Is having the same color of hair only with these three choices, not is it equivalent? Yes, I have the same color as I, so it's reflexive. If I have the same color of you, you have the same color of me. So it's symmetric and transitive again. If I have the same color of you and you have the same color of him, I have the same color of him. Right? So having the same color of hair is an equivalence. What are the equivalence classes? What are the equivalence classes of him? Well, the one with the dark hair, right? And so we can partition. You remember what a partition is? We can partition the student in this class according to the color of the hair. There will be a group of all the students with dark hair, a group of all the students with blonde hair, and a group of all the students with red hair. A student cannot be in two groups. And each student ends up in one of these groups. And so this is a partition. The quotient of a set modulo an equivalence relation are these equivalence classes. And so, how do you represent these equivalence classes? In the case of the color of the hair, you would represent them with the dark, blonde, and red. In the case of being born in the same month, you would represent them with the January, February, March, April, and so on. So there are some interesting facts about this. If this is a partition modulo an equivalence, the intersection of two elements of the partition is empty. You cannot have a student that is blonde and redhead at the same time. It's either one or the other. You cannot have a student that is born in January and in March. Is born either in one or the other. And so, you have that point one. Point two is that when you put all these equivalence classes together, you get the original set. You take all the elements that have dark hair, all the elements blonde, and all the elements red hair, and you put them together, you get all the students in this class. If you put together all the students born in January, plus all the students born in February, March, and so on, again, you get all the students that are in the class. So far, so good?
So, what's the difference between equivalence class and quotient? Because
Equivalence class and
quotient,
quotient. So, the quotient is the set of all the equivalence classes. Equivalence class are all the elements that are related. Should we make some examples? Yes. So, I'll do it here. Let's take all the elements of Z, right? And let me write them in this way. 0, 1, 2, 3, and 4. 5, 6, 7, 8, and 9. 10, 11, and so on. Right? Now I say two elements here are equivalent if when I divide them by 5, I get the same remainder. So let's see a couple of elements that are equivalent and a couple of elements that are not. Who can tell me elements that are equivalent to 1? All right, someone said 6. I would have expected first 1, 1, but 6 is good as well. Right? Who can tell me some elements that are equivalent to 6? $26? Yeah? Who can tell me some elements which are not related? 6 and 7. Why they are not related? Because when you divide the 6 by 5, you get the remainder 1, and 7, you get the remainder 2. They are not equal, so they are not related. Far so good? All right, so what are the equivalence classes here? Columns, very good. This is an equivalence class. This is another equivalence class. This is another, and this is another. How many equivalence classes there are? 5. How many elements in each equivalence class? Of course, an infinite number. What is the quotient of this? The quotient of this is a set that has 5 elements, because the elements are the equivalent classes, and we said that there are 5. Right? And how do we name those elements? Being a bit sloppy, but being a bit clever, I call them 0, 1, 2, 3, and 4. Because these are the reminder when I divide. In fact, this is so common and so popular that we have a notation for this. The notation is here. When I have n, a natural number, with this subscript k, or z with the subscript k, we denote what? The element between the 0 and k minus 1. So in my example, k was 5, so I go from 0 to 4. And I can do operation there, addition, multiplication, subtraction. And when I go over 0, 4, I roll back to 0, 4 by adding or subtracting 5, because if you change a number by 5, you remain in the same equivalence classes. Right? If you look at this one here, how do we go from one element in one equivalence class to the other in the same equivalence class? You keep adding 5, or you keep subtracting 5 if you move the other way around. Yes? So the quotient is the one where you call this 0, 1, 2, 3, 4, 5, and you have it. So we are going to use this when we talk about encryption in a week or so from now. And so this is why we study these things, because when then we do computations, they come about. So far so good? All right, so let's make this a little bit more fun. Today was so there are. So you're familiar with some programming languages like C, C++, maybe you know Python or Ruby. They are very much similar. They have procedures or subroutines or methods. Concept is very close. You pass parameters, get back results, and you have statements like assignment, loop it, while, for, repeat, depending on the language, right? This is one class of language. These are called imperative or object-oriented. Then there are functional languages, where the only thing you do is to define functions, and then you evaluate an expression made with these functions. The model of this one is a pocket calculator. In a pocket calculator, you have functions like addition, square root, logarithm, whatever it is. You put an expression where you add, compute the logarithm, the power, and you get the result. And so there is one class of language that is called logic. And in logic language, the only thing you do is to manipulate the relations. And so, just to motivate you to study the relations and their properties, we are going to write a program in this language and see how it runs. So I call here an editor. Let me go to a directory. Is this large enough, or should I make it a little bit bigger? A little bit bigger. So I write a program that I call match. Oops. And this program is for a dating site. So in this dating site, there are members that subscribe and go there, and they have to fill a questionnaire for what is interesting to them. Like someone likes to speak, and someone likes to play tennis, and then the system tries to match people according to whatever they like. Sound reasonable? All right. So the first is we define a relation that we call likes. And this relation is a subset of the Cartesian product between people and activities. All the binary relations we did so far, the first slot and the second slot were the same kind, both numbers or both students. So here instead we do people and activities. And so here I will like the people that I have, I will give them a name, and the activities are familiar, so I write it this way. Likes, and here I will put the Bob. And what does Bob like? Football. And this is how you put a pair in the relation in my program. Likes is the name of the relation, and then I have a set of people, a set of activities, and I pick a pair. Far so good? And so, this is not a function, so Bob may likes many things, and so what else Bob likes? Beer? Who doesn't like beer? Right? And then what else Bob likes? Let me put another one so we can play with this. Oops, links. Likes. Bob, NASCAR? Enough about Bob? Sounds like a fun guy, right? Does he? No, not really. Say that again?
Who's the third one?
Who is the third one?
No, Sam's the third one, like mix it. If he likes hiking or something. Like
Yeah.
NASCAR.
All right, so now we put there Alice. What does Alice like? I'm going to be very stereotypical.
Bowling.
Say it again?
Bowling.
Bowling. No. She likes flowers.
Oh.
So, what does she like to drink? More stereotypical. Come on. Say that again. Mai Tais. What is it? Like a mojito?
Yeah.
Yes. So I don't know how you write it. So I'll put mojitos here. That's very good. And what else does she likes? Picnics? So far so good? Oh, I forgot Alice. So you already know how to program in this language. All right. Let's put also Doug here. What does a dog like? Football too, right? Real guy. And what also he likes? We'll get there, but he also likes beer. And then flowers now. But he said, really, here, if I want some action, I better like something else. So he likes picnics too, right? Maybe not completely sincere, but so in this language, this is called these are called facts. It's information that you put there. Here, what we are doing here is exactly putting pairs in the relation. So this is the subset of the Cartesian product between people and activities, which we don't specify. But so now I want to put there another relation that I call match. And in this relation there are two people that are being matched and an activity. And this is an activity that they both like. Alright? And so I write it in this way. Match X, Y, and Z. Uppercase are variables, and the lowercase are constants. And so, when we match X and Y, we match them. This one is read if. If likes X, Z, and likes Y, Z. So here, what's going to happen? We pick the two people that like the same thing, and so this is a potential match. So far, so good? So at this point, if I run this one, and I say find an X and a Y that likes Z, what do you think is going to happen? Say that again? Right, that's fantastic. Bob and Doug are both like football, so this would be a good match, right? Perhaps it was not intended, not that there's anything wrong with that. So we may have to make it, but there is something else even before that.
Bob likes football and Bob also likes football.
Say that again?
Bob likes football and Bob also likes football.
Right. This is going to be some kind of reflexive. Bob likes Bob because they both like, and so here I had something else. Not only, we are going to find that Bob likes Doug because they both like football, and Doug likes Bob because they both, this is also symmetric somewhat, right? So I have a way to fix it a little bit, and I say, look, X has to be less than Y. I write it in this way. And this is done according to some order that here I don't care very much, actually will be the alphabetical order. But this is going to prevent Bob from liking Bob, because Bob is not less than Bob. And if I find that Bob's like Doug, I'm not going to find that Doug's like Bob, because it's not symmetric. Alright, so now we can run it. and see what happens. So the language is called Prolog that does this. And now I load this program that I have to write it this way. And now I say match X, Y, and Z. And as we expected, Bob likes Doug because they both like football, right? At this point I say, I don't really like this match. I do this by putting a semicolon. And he's trying to find another one. Ah, Bob likes Doug because they both like beer, right? Ah, finally, Alice liked Doug because they both like picnic. Doug was very smart at putting picnic there. I can say, give me another one. But says, no, there are no more matches based on what they like. While functions, you give an input and you get an output. We didn't talk about this with the relation. In the relation, there is not an input and an output. There are pairs, right? And so this language understands this well. So here I can say match Alice, let me call it U and V. The name really doesn't matter. And so here is trying to find a U and a V that we can match with Alice. And so if I do this one, it says the Doug and picnics for U and V, and there are no other options. All right? I can do it in other ways. I can say match X, Doug, and Z. And here is trying to see what are the matches for Doug, both the people and activities. And says the Bob and football. And should have found... oh, I didn't put the semicolon. Thank you. Oh, you know everything about this language. All right. So now I put the semicolon and give me the beer. And now, oh, also the picnic. Yes. I could say I want to find a beer buddy for Bob. So I say Bob, X, and beer, and we'll find Doug and no one else. So you see how I do these things? And so this is based on relations. There is no assignment, there is no looping, there is nothing else, but you can compute everything you want. I can write a quick sort in 2 lines in this language. I can write a function that computes the factorial or Fibonacci or whatever you want. So you can compute almost anything you want. But the only thing this language does is relate, nothing else. And so this is why we care about the relations. Far so good? So I hope this motivates you a little. I hope it was also fun. All right. So I wrote here that the homework 2 is due on January 30. We agree on that. And we can start to move on algorithms. Is there any question before we move on? All right. So I won't insist much on this because I expect that most people know the basic of algorithms. What is an algorithm? is a sequence of executable steps or instructions, if you want. The execution must be finite. If we cannot guarantee that the execution is finite, we don't call it algorithm. We use different names, but not algorithm. Deterministic. Deterministic means that the output of each step has to be precisely defined. There is no chance. However, the language that I just showed you is non-deterministic. Typically, we have input and output. How do we present the algorithm? Code or pseudocode? Typically, you don't write the algorithm in English. You write a theorem in English, or the proof of a theorem in English. But an algorithm is different. So here we have an example of an algorithm to compute the average of two numbers. So first there is an input, A and B are numbers. Then there is that assignment or computation where C is the sum divided by 2, and then you output C. What do you have in algorithm? In this kind of languages, you have assignment, conditional, what is conditional? If, then, else. Repetition and input output. Sometimes, even with algorithm, we consider what is called procedural abstraction, where you make a call to some method, function, subroutine, and you match the argument, and then you get a result. So far, so good? Not terribly exciting. You should have known all this. Now, some algorithms are recursive. And what is a recursive algorithm? In the recursive algorithm, there is some procedure or function or method that at some point makes a call to itself. And sometimes this is difficult to understand, and you have to be careful that when you make a call to itself, shouldn't eventually go to the same point and make a call to itself, and should eventually go to the same point and make a call to itself, and never return any. Alright? And so here there is an algorithm to compute a power of some number, where the exponent is an integer. And so we write it with those two lines. You can write it the same in your favorite programming language. And so let's try to understand that. What does it say? Say, if I have to compute the 0th power of a number, the result is 1. If the exponent is n plus 1, so can't be 0, how do we do it? We compute it for n. You multiply by 8, and this is the result. Should I trace it so we understand it? Suppose that I want to compute 7 to the third. And let me write here the equations. So you with me? So how do we compute this one? We distinguish between these two cases. Which one are we going to pick? Well, 3 is not a 0, so we cannot pick the first, right? So this is what? This is 7, 2 plus 1. You with me? So we apply this one, and this one says what? Take 7 and multiply by what? 7 squared. That is the general rule. I am applying this one to 7 to the third. And so now I have to compute this one here, right? So 7 to the second. 2 is not a 0, so I have to apply this line, right? So is 1 plus 1 equal to what? Times 1. You with me? And so now I have to compute the 7 to the 1, which is what? 0 plus 1, because it's not a 0. So what do we get? We get 7 times 7 to the 0. And so what is 7 to the 0? 1. So this 7 to the 1 is 7. What is 7 to the second? 49. So this one is 49. What is the result? 7 times 49. I can't do it in my head. But, so far so good? So there are a lot of beautiful algorithms that are done recursively in this way. You probably know the same, right? To iterate is human, and to recur is divine. I know, they should be better, but I said this earlier. All right, so we can see factorial. Factorial is very similar to this. How would we write a factorial? Factorial of where we start? 0? Oh, yes, thank you. 0 or 1? We start at 0 typically. Factorial of 0 is 1. And here I have the factorial, and I write it exactly as we did before. N plus 1. And so what will be this one? Let's look at the one over here. Here, to do the power, I say the power n plus 1 is the base, the power n. The factorial of n plus 1 is what? N plus 1 factorial of n. So typically when you do recursion on the natural number, you consider the case 0 and the case n plus 1, which cannot be 0, and you say what to do here. Yeah? You with me? We can do this with other structures rather than the natural numbers. And I want to make a couple of examples. Suppose that we want to concatenate strings, right? Like sequences. So here I have the sequence A, B, C, and D, E, F, and I want to compute A, B, C, D, E, F. I stop putting the quotes because the only thing I'm doing is with a string, right? So a string can be empty, which corresponds to the 0 of the number, or can be what? One character and a string, which is like before. If I have an n, a number which is not a 0, is 1 and a number. You see the similarity between the two? So if I have to compute that one, the two strings, how do I do it? I will say this one. I represented this one with a plus plus because in many languages this is the way this is denoted. So if you have the empty string plus plus a string x, what is the result? X, right? Here you can think about adding 0 to a number. If you add a 0 to a number, you get what? The number. So concatenating the empty string to a string, you get the string. The other case is that this string here is one character, follow, let me write it this way, by some other characters, which I don't know what they are. This means I have a string which is not empty. There is one character which I represent with A, and there is another string that I represent with Y. If I concatenate, what do I get there? Someone said it? A, and then I have to concatenate Y and X. Should I do it graphically? Which may help understanding. So let's do it for the example above. Here I have my string where I have A, B, and C. And here I have D, E, and F. So I have to make the first step, right? So what do? I have this A here, and then I have to concatenate B and C with D, E, and F. You with me? I'm just applying what I wrote here. And so now what do? I have to compute this one. This one will be B, followed by what? C concatenated with D, E, and F. Yeah? So now I have to do this one. What do? I have C followed by what? The empty string, because now I don't have anything, concatenated with D, E, and F. What is this one? This one I go up to this case and say, look, if you concatenated the empty string, it's just the second one. And so what does this becomes? C, D, yes, thank you, E, F. These two are the same, right? So now I can do this one because I found the value of this one here. So this one becomes what? B, C, D, E, F. And so the last one will put the A in front, and now I have this one. There is not the plus plus anymore. All right? Yes?
Would it be required to diagram or pseudocode any algorithms like this in class?
We will do it in class. Are you mean in a test?
Yeah, particularly.
In a test, you just fill a bubble. So.
Okay. I guess my question is, so you go down to the most case of empty string.
Yes, you have to.
Okay, rather than the one before it,
Yes.
which you have an implied answer.
Yes. Yes. So what if I write? So I want it because it's getting too long. So before I close this one, any question? So next week you have a question?
I would say the test is on Wednesday, right?
Right, I was going to talk about that. So on Wednesday we have the exam. So for the exam you need the Scantron form, and you have an example here. Yes? This is the Scantron form. There are equivalent, but basically the number is here, 8A2E. Bring it here.
Where do we get it?
The bookstore. Probably also other places, but the bookstore has it. And I would encourage you to read a little bit the stuff about the exam, so you come here and you are prepared, and I'd be happy to answer any question. Yes?
Will Monday, the stuff we cover on Monday, will that be part of the evening as well?
No. Actually, I think even this on the other it will not. So the content will be up to, maybe I should put it online, up to section 2. A review on Monday? Yes. No, I wasn't planning, but because we do the review every time on the previous material. But come with questions. And if you have questions or if you want to review something, I'll be happy to do it. Yes? I'm sorry, say it again. I'm a little deaf. I can't hear you. So, section 1 and section 2. And also, we skip a week, so why don't we let me go back and show it clearly? So, if we look at the schedule, we have section 1 logic and section 2 that has sets, functions, and relations. So, I will do this one. And relation here also. All right, section 1 and section 2. Any more questions? All right, have a great weekend.
I did want to clarify.
Say that again?
I wanted to clarify something
Yes.
from your relations real fast. So in your thing you had in the slides, you had, so if you have the quotient where it's modulo and the result is like
Yes.
equivalent sets of 0 through 4, and you said 2 minus 4 equals 3. But earlier you said that we're going to be very particular about saying equivalent to. So would it be in this class, could we get marked down for saying
Yes.
equal rather
No,
than...
no.
Okay.
Come on. I'll make it clear if I want this or that.
What's the time scan from doing? The link on the website is
No, is there. All right, I'll check it. Send me an email. Are you sure that... I don't understand why it's not there. It should be there. But I'll verify it. The network never works well here. All right, so let me go to the website, local page, computer science, courses, discrete structure, landing page, exam, Scantron form, not found. You are right. So I'll fix it.
All right,
Thank you.
So where can you find the recorded lectures, the classes?
So it's written here. I don't think I can tell you and you are going to remember it. So here said recorded lectures.
Okay.
And so here is telling you how to do it and what to do if it doesn't work.
Okay. Okay. Thank you.
You're welcome.
potentially just a silly question that caught me right as you were asking for questions, and then you moved on to the next section, and I caught it right as we were moving forward. When you were showing equivalence with quotients,
Yeah.
you wrote down one set which was, I think, 27 and 6. Or 6 and 26 right here. I was
Yes.
just curious because this was when you're you're finding the remainder after dividing by 5.
So,
Um,
yes.
So my question is, how could you have 6?
6
and-
divided by 5 is 1.
Right,
The
so
remainder.
that's-
And
so-
26 divided by 5, the remainder is 1.
Okay. That's just.
You can
that
keep
is-
it or whatever.
No, actually, that answers my question. It just showed that I
Yes.
just realized I didn't quite understand equivalence.
All right.
Just as far as what could go with what, I thought it was.
Yes.
actually whatever is equal to the.
Uh-huh.
Okay.
All right.
Thank you.
You're welcome.